A very good evening, my dear friends, and a warm welcome to this session on India's largest online live learning platform. My name is Rushi Joshi. You are watching me on Gradeup GATE YouTube channel, my dear friends. How are you all? Am I audible clearly? Very good evening to all of you. Yes, my dear friends, Hemant Nagarajan. Am I audible clearly? Hello, Ramiz. How are you? Good evening, Nagarajan. Is my voice clear to all of you? Please respond, my dear friends. Good evening, Imtiaz. Cold evening, Nagarajan. But here at our place, cold is very less. So, my dear friends, today's topic that is from strength of material, and the topic is about the stresses in beams and shaft. So, my dear friends, yesterday's class we have seen shear force and bending moment, where we have seen how easy it is to find the shear force and the bending moment, my dear friends. Because I have already shared on the Telegram app. Imtiaz, I have shared on Telegram app. So I will just check it out and tell you that on which app I am sending it. Just a minute. So very good evening, my dear friends, and a warm welcome to all of you once again. And so before I start this, I would just like to introduce myself. My name is Rushi Joshi. I have got around 16 plus years of experience in training aspirants preparing for competitive exam. I have mentored more than 25,000 plus engineers across India. This is my GATE score in the year 2002. Engineering mechanics, strength of material, and machine design are the subject of my expertise, my dear friends. I will just do that. Just a minute. On this, I have shared, my dear friends. You have seen the link. Right. So, my dear friends, already we have seen yesterday the shear force and the bending moment. So, we have already seen that shear force is an unbalanced force, and bending moment is the unbalanced moment. Hemant Nagarajan, I will just talk about that in the middle of the class. So, bending moment is the unbalanced moment that yesterday we have seen. So, unbalanced moment. So, my dear friends, we have seen a point where the shear force is equal to 0. So, the point at which shear force is equal to 0 implies that the shear stress tau is equal to 0, means the bending moment is maximum. Bending moment is maximum, and that point is called as pure bending. That point is called as pure bending. Is it clear now? So my dear friends, you see the point where the shear force is 0, that point has got the maximum value of the normal stress, and that normal value is called as sigma b, that is the bending stress. Is it clear? So this is the point we are interested, my dear friend, right? Very good, very good. So this is the point where you see that the normal stress is maximum, and that too sigma b, that is bending stress, will be there where the shear force is equal to 0. So our interest is the point where the bending moment is maximum, and that point is called as a pure bending condition. So what is that pure bending condition, that I will see. So we have seen that the bending moment which was started with linear curve. So whenever there is a point load which is acting, point load, you see that the shear force diagram is a constant line, and the bending moment diagram is linear. So my dear friends, when I talk about the bending moment diagram which is linear, when the bending moment diagram is linear, no two points has got the same bending moment. So when I talk about the section 1 and section 2, so the bending moment in 1 is not equal to the bending moment in 2. Is it clear now? So bending moment is not equal in these 2 points. So we have to focus on the point where the shear force is 0, means your bending moment is maximum, and that too constant at that point. Is it clear to all of you? So let me tell you what is that value. Let me tell you what is that value of the pure bending condition, my dear friends, and the constant value of the bending moment. And once we can find out the maximum and the constant value of the bending moment, and that point will be having the maximum value of the stress, we call it as bending stress, my dear friend. Is this clear to all of you? So my dear friend, very fastly click the like button, share with your friends, subscribe the video, and don't forget to press the bell icon, my dear friends. Let me start now. Shall we start now? So my dear friends, when I talk about the pure bending condition, so this is the point A, point B, point C, point D, and the reaction at B and C. You see that the reactions are equal to W and W. So what will be the shear force, my dear friends? The shear force at A is equal to, the shear force at A is equal to, one value is 0, and the shear force at A, another value, is equal to minus W, and the shear force at D is equal to 0, and the another value of the shear force at D is equal to plus W. Is it clear now? And after that, when you see the shear force at B point, it will be again from minus W to this, so it will come back to 0, and shear force at C will also come back to 0, my dear friends. And this is what the shear force diagram, it is varying from 0 to minus W, from minus W to 0, and here it is 0 to plus W, and constant plus W to 0. And you see that the point between BC has got shear force equal to 0, implies that the shear stress is equal to 0. When the shear stress is 0, this portion is called as pure bending. So pure bending means when I draw the bending moment diagram here, what is the value of the bending moment at A? Bending moment at A is also equal to 0. Bending moment at D is also equal to 0. But what is the bending moment at B? It is equal to minus W into A, and bending moment at C is also equal to minus WA, and that too constant bending moment. So this is the point B where we have got the same value minus WA, means this is the portion which has got a constant bending moment, Is this clear to all of you? So this portion of the beam BC is called as pure bending. So the portion BC of the beam BC of beam is called as pure bending. Is called as pure bending. Is it clear, my dear friends? So what is happening in bending, my dear friends? What is happening in bending? There is no shear stress. There is no shear stress, only bending is happening, my dear friends. What is happening in bending? Can you tell me? Means the beam will be deflected in such a way that the top fibers are subjected to compression and the bottom fibers are subjected to tension, whereas the neutral fiber remains same. So if you see the beam, where we have got a constant bending moment between DC, it has got a constant bending moment between BC. You see that constant bending moment between BC. You see that the top fiber AD is compressed. So you will be getting the bending like this. AD is compressed to A dash D dash and BC is expanded to B dash C dash. Is it clear now? Whereas the neutral axis remains same. So it is B dash C dash. Whereas the neutral axis will remain same. So this is the point where you are getting the neutral axis, my dear friend. Neutral axis which remains same. Is it clear now? So this is how we are considering here. So the bending moment at these 2 points BC is assumed to be constant. So we get the value of the bending stress, and this R is the radius of the curvature. So sigma upon Y is equal to, or sigma upon E is equal to Y by R. So from this, sigma upon Y is equal to E upon R, and I also know that when I relate it with bending moment, that is the moment of resistance. So M by I is equal to sigma by Y is equal to E by R is the pure bending relation. Is pure bending relation or flexural stress formula. Is this clear, my dear friends? So this formula already very well everybody is aware of. So from this I am calculating the value of the bending stress. What is the value of the bending stress? Bending stress is equal to M upon I into Y. M upon I into Y. So sigma B will be maximum where the bending moment is maximum. I value will be same and Y will be equal to Y max. So this can be written as M upon Z. M upon Z, where Z is equal to section modulus which is equal to I by Y maximum. So all our beams stresses are depending upon the Y upon Z value. Is this clear to all of you? Is this clear? So our focus should be on section modulus of the beam. Suppose if I consider two types of beams, so if we consider two types of beams, one, let it be a cantilever beam subjected to a square cross section. This is first beam, and the second subjected to a circular cross section. Like this. So my dear friend, you see that the bending moment in these two cases will be same. So the bending moment in 1 is equal to the bending moment in 2, because it is just load into the perpendicular distance. So length of this is same, load is also same, my dear friend. So the bending moment in these two cases is equal to, so the maximum bending moment is equal to P into L. Is it clear now? Is equal to P into L. So the bending moment is same, my dear friends. So what is the difference here? Your section modulus is variable. So your bending stress is equal to M upon Z. So implies that the sigma B value is inversely proportional to section modulus. If Z is small, the bending stress is more. When the stress is more, the beam is weaker. The beam is weaker because stress is more. Because stress is more. Is it clear now? So if Z is large, the stress sigma B is less, hence beam is stronger because it is subjected to less stress. Is this clear to all of you now? So this is what is the criteria where we can find out the value of the beam subjected to either a maximum stress or a minimum stress. So generally the question will be which of this is subjected to more stress, which of this beam is subjected to less stress, and which of this beam is stronger, which of this beam is weaker will be the question asked to you, my dear friend. Is this clear? Hello Shushmita Das, how are you? Yes, my dear friends, not seeing any Josh from you, no response. Yes, come on, my dear friend, cheer up. So now you see that your sigma is inversely proportional to Z, right? So sigma upon Y is equal to M upon I. So M upon I is constant. So sigma is directly proportional to or is equal to M by I into Y. Is equal to M by I into Y. So my dear friend, this equation is a linear equation. So sigma is directly proportional to Y. So this is called as a linear curve. Linear curve means the stress which is distributed across the cross section will be linear with neutral axis having a zero value. So my dear friends, you see that this is what is the neutral axis. This is what is the neutral axis, and this is the point which has got the maximum value of y maximum. So my dear friend, at neutral axis y is equal to 0 implies that the bending stress is equal to 0, whereas at the top and bottom fiber y is y max, hence the bending stress is maximum. So at the top fiber and the bottom fiber, the bending stress is maximum. Imtiaz, let me complete that. I will send you the PDF as I told you already. Clear? Don't worry. I have sent you the link. On that, I have sent you the link. You can see the link is been sent by the name Manasvi Joshi. Is it clear? Is this clear? Shall we proceed? So my dear friend, let's see the distribution, how it is being distributed. Right. So when I see a rectangular cross section at neutral axis, the sigma b value is equal to 0, So if it is a simply supported beam, my dear friend, you see that the top fibers are compressed, whereas the bottom fibers are expanded, my dear friends. So this is what is the cross section that I am taking. So you see that the top fibers are subjected to compression, whereas the bottom fibers are subjected to expansion, with neutral axis remaining the same. So this is what is the distribution, my dear friends. So the stress on neutral axis is equal to 0. The stress on top fiber is equal to compression maximum, and the stress in the bottom fiber is equal to tension stress. Is it clear now? So this is how the stress has been distributed. At the top fiber it is maximum compressive, at the bottom fiber it is maximum tension, and the value of the bending stress is equal to minus m by I into y, and this is equal to m upon I into y maximum. Is this clear? Right. So this is what the distribution that you have to see, my dear friends, in the beam. So since bending stress is directly proportional to y, so at neutral axis y is equal to 0, means your bending stress will be equal to 0. At top and bottom fiber y is maximum, so the bending stress is equal to maximum, my dear friend. Is it clear now? So on one side it is maximum compressive and other side it is maximum tensile, right? So now let's see that only one point where the shear force is 0. This is what we need to understand. So if the shear force is equal to 0, then you get the bending stress as m by I into y. Why? Because we are getting a constant bending moment. But what about the other points? Other point has got some shear force. When other point has got some shear force, obviously the bending moment, obviously there will be some shear stress which is induced. Is it clear now? So there is also a shear stress in the beam. Now what is that shear stress in the beam? Let's see now. So when I talk about the shear stress, so since with point load, the bending moment is linear. So no 2 points on the bending moment has same bending moment. No 2 points, or I can write down in this way that the bending moment is not constant. Implies that the bending moment is not constant. So bending moment is not constant means that the shear force is not equal to 0, implies that the shear stress is also not equal to 0. So obviously there will be some shear stress. Is it clear now? So let me take an example here about this, that when there is a pure bending, what is the meaning of pure bending? Shear force is equal to 0 means shear stress is also equal to 0. This is called as pure bending condition, my dear friend. But when you see that there is bending, so when you apply a shear force, when the shear force is not equal to 0, means the shear stress tau is also not equal to 0. So there is some shear stress which is induced in the beam, my dear friends, And what is that shear stress? That let's see now, right? See here, if it is a simply supported beam, Imtiaz, if it is a simply supported beam, then you see that the top fiber is compressed, bottom fiber is expanded, so it will bend like this. Is it clear now? So यहाँ पे आएगा आपको compression आएगा ऊपर में और यहाँ पर आएगा tension आएगा नीचे, ठीक है? This is for a simply supported beam. But for a cantilever beam and subjected to load, you see that the top fiber is expanding, whereas the bottom fiber is compressing. The bottom fiber is compressing. So this is tension and this is compression. Is it clear now? So it depends upon the type of beam and type of loading. Is it clear? Type of beam and type of loading. So shear stress is equal to 0, pure bending. If not, then you will get shear stress also. And what is the magnitude of the shear stress? That is what we are discussing, Nagarajan. So if shear force is not equal to 0, means the shear stress in the beam is also not equal to 0. Means the beam is subjected to shear stress also. Is this clear? Now let's see what is the magnitude of the shear stress. So my dear friend, for example, if I take a section AB and section BC, everybody know that these two portions of the beam has got different bending moment. So the bending moment in AB is equal to M and bending moment in CD is equal to M plus DM. Is it clear now? So when I talk about AB and BC, when I talk about AB and CD, this is AB, this is CD. So can you tell me what is the value of the stress in AB and what is the value of the stress in CD? What is the stress in AB? So the stress in AB is equal to how much? Yes. So can you tell me what is the value of the stress in AB? It is equal to the bending moment on this section is M. The bending moment on this section is M. So the bending stress on AB is equal to M upon I into Y. Right. So it is equal to sigma AB. Now what is the value of sigma CD? Sigma CD is equal to M upon I, M plus DM upon I into Y. Is it clear now? So you will be getting the stress on this CD as M plus DM upon I into Y. So my dear friends, there is some difference in the stresses. So the unbalanced stress is equal to sigma CD minus sigma AB, which is equal to DM upon I into Y. Is it okay to all of you? DM upon I into Y is called as the shear stress. Is called as shear stress. So the extra stress which is developed on CD is called as the shear stress. So you see that, my dear friends, there is a magnitude of the shear stress which is developed on the section CD. We call it as tau vertical. Is it clear now? So this I write down it as tau vertical, which is equal to DM upon I into Y. Right? So everybody know that shear cannot be alone. Shear cannot be alone. It is always accompanied by a complementary shear in a perpendicular direction. Agree? So my dear friend, this tau vertical cannot be alone, and develop tau horizontal also. That is complementary shear stress. Everybody agree to this? So my dear friends, you see that there is one more shear which is developed, that is called as tau horizontal. Is it clear now? So now we need to balance tau vertical as well as tau horizontal also. Now who is taking care of tau vertical? Who is taking care of tau vertical? The loading given in the problem is balancing this tau vertical, but nobody is there to balance your tau horizontal. So the beam strength, the capacity of the beam should satisfy that. Is it clear to all of you? Yes, my dear friend, please respond. Since there is a difference in the stress on two sides, AB and CD, there is a difference in the stress equal to dm upon I into y, and that stress is called as unbalanced stress, and that stress is the shear stress in the beam, which we denoted by tau vertical on CD. Agree? Right? So now this tau vertical, before it get balanced, it has created a complementary shear in a perpendicular direction to this tau vertical. This is your tau vertical. So before this tau vertical get balanced, it has created a complementary shear in the horizontal direction called as tau horizontal. Agree to this? Now we need to balance tau vertical as well as tau horizontal also. So who is going to balance tau vertical? The loading that you are giving in the beam is balancing tau vertical, whereas nobody is there to balance horizontal. So this horizontal shear stress is disturbing the beam. So tau vertical is developing a complementary shear stress, a complementary shear stress called as tau horizontal. Is it clear now? So it cannot be alone. It cannot be alone. It cannot be alone. Is it clear now? So just I will explain you in this. So my dear friends, if this is the beam, this is the beam, this is the cross section. So this is the cross section. These two are the cross section. So my dear friend, on this side you see that there is a bending moment M. On this side there is a bending moment M plus dm. So obviously the stress on this CD will be more, and that magnitude is equal to dm by I into y. So you are getting more stress here, and the leftover stress we call it as shear stress. Unbalanced force is called as shear force. Unbalanced stress is called as shear stress. So my dear friend, when I take the shear stress vertical, everybody know that it cannot be alone. It is always accompanied by a complementary shear in the top fiber that is perpendicular to the vertical. Is it clear now? Sir, how can we tell that it is compressive or tensile? I am not talking about compressive or tensile. Kajal, I am not talking about compressive or tensile. Right? Is this clear now? I am just talking about shear. I am just talking about shear. Since the bending moment is different in two portions of the beam, that is AB and CD, there is some extra leftover stress called as shear stress on CD. On CD. Is it clear now? So that shear stress, before it get balanced, it creates a complementary shear in the perpendicular direction, that is the top fiber. That is the top fiber. So the formula for the shear stress, in the beam, I am just writing the formula for the shear stress in the beam. Tau is equal to SA y bar upon IB. Is it clear now? So S is called as the shear force. S is called as the shear force. Shear force. A is the cross sectional area. A is the cross sectional area. Y bar is called as the centroid point of the element. I is called as the moment of inertia about x-axis, and B is called as the width of the beam. Width of the beam. Is it clear now? So this is what the formula, general formula to find out the shear stress in the beam. Is this clear? But our interest is something different. Clear, my dear friends? Any doubt up to this? Do you have any doubts? Yes, it is area moment of inertia, Naveen. It is area moment of inertia. Is this clear? It is area moment of inertia. Right, I have shared the link in this group, my dear friends. You can just download the Telegram app. I will be sending all the PDFs of the classes from last 3 and today's. Power, listen here. So you see that this is the beam, this is the portion AB, and this is the portion CD. Please focus here, my dear friend. The bending moment on AB is M. The bending moment on this is M plus DM, some extra bending moment here. So obviously the stress on this is M by I into Y. The stress on this is M plus DM upon I into Y. So when I talk about this section and this section, there is a difference in the bending moment, and the difference in the bending moment is equal to DM divided by I into Y. You can see here. So that extra bending moment is called as tau vertical. Unbalanced stress is called as shear stress. So dm upon I into y, that is the difference in the stress in AB and CD, is called as tau vertical, which is shown by my hand. Is it clear now? But everybody know that tau cannot be alone. It is always accompanied by a complementary shear in a perpendicular direction. So there is a complementary shear which is developed here. You can see my horizontal hand, left hand, right? So this is called as a complementary shear, called as tau horizontal, which is developed on the top fiber of the beam. Is it clear now? So now we need to balance both. Tau vertical also we need to balance, tau horizontal also we need to balance. So who is taking care of tau vertical? The loading that you are giving in the problem is balancing that tau vertical. Is it clear now? So the loading that you are giving in the problem is balancing your tau vertical or vice versa, but nobody is there to balance horizontal. So this horizontal shear stress is disturbing the beam. Is it clear to everybody? And the formula for that is SA Y bar divided by IB. Right? So it is on Telegram channel, Hitesh. So is this clear, my dear friends? Now let's see the distribution for a rectangular cross section, a circular, and this one, my dear friends, one by one we'll see. So generally we need to remember just one or two formulas there. So the shear stress in beam for a rectangular cross section is equal to tau, which is equal to 0 at top and bottom fiber of the beam, and tau is maximum, which is equal to 3 by 2 times S by BD at neutral axis. So the distribution for a rectangular type of cross section is, this is neutral axis. So the distribution for this will be, we call it as shear stress distribution. Shear stress distribution. So at the top fiber the shear stress is 0, at the bottom fiber the shear stress is 0, but at the neutral axis it is maximum, and that is a parabolic distribution, my dear friend. So the distribution will be something like this for a rectangular cross section. So tau is maximum, which is equal to 3 by 2 times S by BD, which we call it as tau average. Is it clear now? Hitesh, I will send it today once again. Don't worry. This is for a rectangular cross section. For circular cross section, tau is equal to 0 at top and bottom fiber, and tau is maximum, which is equal to 4 by 3 times tau average. So for a circular cross section, you see that the distribution will be, it is 0 at the top, 0 at the bottom, and maximum at the neutral axis, which is equal to tau max, which is 4 by 3 times S by pi r square, right? And for a triangular cross section, this is the center of the beam, and this is called as the neutral axis. Neutral axis is at a distance of h by 3 from the base and 2h by 3 from the apex. Is it clear now? This is 2h by 3 from the apex and h by 3 from the base. So your distribution will be tau is equal to 0 at the bottom fiber, tau is equal to 0 at the top fiber. At this point it is maximum. So tau is maximum, which is equal to 3 by 2 times S by half base into height. We also call it as 3 by 2 times tau average at center of the beam. But at neutral axis, your tau at neutral axis is equal to 4 by 3 times tau average at neutral axis, that is the centroidal point. Is it clear now? Very good, my dear friends. So at center it is maximum, but at neutral axis it is 4 by 3 times tau average. So this is what we need to remember, my dear friend. Is this clear to all of you? My dear friends? Yes, come on, my dear friend, cheer up. Clear? Now, my dear friends, let's see what is the value of the shear stress in the shaft. So, my dear friends, I will just consolidate beam. So, in beam problem, if shear force is equal to 0, then you get the bending stress, which is equal to m by I into y. And if the shear force is not equal to 0, we get the shear stress in the beam as ESE y bar divided by IB, and tau is maximum, which is equal to 3 by 2 times tau average for a rectangular cross section, and tau is maximum, which is equal to 4 by 3 times tau average for a circular cross section, and tau is maximum, which is equal to 3 by 2 times tau average for a triangular cross section at center, and tau at neutral axis is equal to 4 by 3 times tau average at centroid of the triangle, at centroidal axis of the triangle. Is this clear now? So here, my dear friends, these values are also equal to tau at neutral axis. In rectangular, this is also called as tau at neutral axis. So in this case, tau maximum and tau neutral axis are same, but here you have got different values, tau maximum and tau neutral axis. Yes, so my dear friends, don't worry. In our competitive exam, more than 90% they will ask you only these three types of cross section. One is rectangular, one is circular, one is triangular. Otherwise, if for other cross sections, you can take tau as SA y bar divided by IB and find the values and find the value of the shear stress. Only these three you remember. Only these three you remember. For other cross section, no need to remember. So you have to remember this formula. 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 These are the formulas that you need to remember. If other than this, if something is asked, then you have to use SA y bar divided by IB. Is this clear? See, Kajal Mangal, it is the derivation that you are getting it. Since time is very less, there is no necessity of taking the what we call derivation part of that. So if you want to find out, see how the derivation is been done, you can just go through the app where I have taken so many other classes, and there you have seen the stresses in the beams also. Is this clear? Right. So now let's proceed for the shaft. So when I talk about the shaft, my dear friends, when I talk about the shaft here, you can see that this shaft, when subjected to a twisting moment, you see that this AC, which is having a length L, is shifted to BC, and this angle is called as phi, and this phi is called as shear strain. Shear strain. So what is the value of shear strain? The shear strain phi is equal to AB upon AC. This is change that you are getting it divided by the original length L. So change in one direction divided by the original length in the perpendicular direction is called as shear. When I see the side view of this shaft, then this angle is called as angle of twist. So theta is equal to angle of twist. So because of the torque T, A is shifted to B. So can you tell me what is the arc length AB? Arc AB is equal to how much? Can you tell me what is the value of AB? Can you tell me what is the value of AB? Yes, my dear friends. Can you tell me what is the value of AB? AB is equal to R times angle of twist theta. So this can be written as R theta divided by L. Is it okay? R theta divided by L, my dear friends. So what is shear strain? I know that tau is equal to G times phi. So phi is equal to tau by G. Is it clear now? Tau by G. So this is 1, this is 2. Equating 1 and 2, we get the value as tau by G is equal to R theta by L by equating 1 equal to 2. Implies that the shear stress is equal to G theta upon L into R. So the shear stress is directly proportional to the radius. At center of the shaft, at center R is equal to 0. implies that the shear stress is equal to 0 at outer periphery R is maximum, then tau is maximum, which is equal to g theta by L times R, right? R is also equal to T by J into R. Since T by J is equal to tau by R and which is equal to g theta by L. Is it clear now? By this formula. So by this formula. Is this clear? Yeah, it is angular displacement. It is angular displacement, Nagarajan. So the maximum shear stress is equal to this. Clear? Yes, my dear friends, come on very fastly, click the like button, press the bell icon, my dear friends. So now let's see one more conclusion here. T by J is equal to tau by R is equal to g theta by L. So from this, my dear friends, the shear stress is equal to T is the torque, J is the polar moment of inertia, R is the radius. So tau is maximum, which is equal to maximum torque divided by J into R maximum. So this is also equal to T maximum divided by J by R max, and J by R max is called as the polar modulus. So this is equal to T upon ZP, where ZP is equal to polar modulus, which is equal to the polar moment of inertia divided by the maximum radius of the shaft. Yes, Nagarajan, what is that you want me to repeat? What is that you want me to repeat? So my dear friends, this is called as the shear strain. That shear strain is equal to tau is equal to G times shear strain, right? So from this you get one formula, that is phi is equal to tau by G and is also equal to AB by AC. This AB is the change in one direction, AC is the original length in the perpendicular direction. Means AC has changed to BC. Got it? Now when I see the side view, I can find out the length of AB, and length of AB is equal to R theta. So this can also be written as R theta by L, and tau by G, these two can be equated. When you equate these two, you see that the shear stress which is induced in the shaft is directly proportional to the radius. Right? Directly proportional to radius. So at the center of the shaft, radius is equal to 0. Hence the shear stress value at the center is equal to 0. But at this fiber, tau is maximum. Is this clear now, Nagarajan? Is this clear? Naveen? Shafia? Hello? So let's proceed for some questions, my dear friend. Okay, welcome, my dear friend. So let's proceed for some questions on beams and shaft. So the first question on your screen. A beam cross section is used in two different orientations, right? Bending moment applied to beam, both the beams are same. the maximum bending stress in case of A and B are related as. So let this be A and this be B. So the bending moment in A is equal to the bending moment in B. Bending moment in B, which is equal to M, right? Now they are asking what is the value of the bending stress in A and B. What is the value of the bending stress in A and B? Come on, my dear friends. So the bending stress in A is equal to M upon I into Y, right? So now you see that this is neutral axis. So this is called as Y, and Y is equal to B by 4. So this can be written as M is the bending moment, I value is BD cube by 12. So B into B by 2 whole cube divided by 12 into Y value is B by 4. So you will be getting the answer as this B and this B get cancelled, and this will become 4 ones, 4 threes. So this will become 3M upon B cube by 8. B cube by 8. B cube divided by 8. So it will be 24M upon B cube. Is it clear now? This is first. Now your sigma B. The stress in B is equal to same M upon I into Y. And what is the value of Y now? So Y value is equal to B by 2. Y is equal to B by 2. So which is equal to M upon I value is B by 2 into B cube divided by 12 into B by 2. So B by 2 get cancelled. This will become 12M upon B cube. So what is the value of sigma A? Sigma A is equal to 2 times of 12M upon B cube, which is equal to 2 times of sigma B. Is it okay now? Very good. So the right answer to this question is B. B is the right answer, my dear friend. Now can you tell me one question here? Which of these two is stronger? A or B is stronger? A is stronger or B is stronger? A is stronger or B is stronger? Yes, my dear friends. Can you tell me one more question? A is stronger or B is stronger? A is stronger or B is stronger? Yes. So if the bending stress is less, the cross section is stronger. Hence, sigma B is stronger or B is stronger. Is this clear now? So my dear friend, if bending stress is less, then it will be stronger. Very good. Very good, my dear friends. Right. So next question, my dear friends. A horizontal beam with square cross section is simply supported with sides of a square horizontal and vertical. So the first beam is having a sides of a square horizontal and vertical. So your beam is like this. This is your first beam. This is your first beam. And second beam is the diagonal are horizontal and vertical. This is second beam. This is second beam. So it is having a square section, cross section, horizontal and vertical. So here the bending moment is M. Here also the bending moment is M. Right. So here the bending stress in 1 is equal to sigma. They are asking what is the value of the bending stress in 2 is equal to. What is the value of the bending stress in 2? Yes, we can also use BD square by 6. Deepak Kumar, we can also use BD square by 6. Yes, my dear friends. So your sigma B of 1 is equal to M is the bending moment. I is equal to the side of this square is A. The side of the square is A. So it is A to the power of 4 divided by 12 into A by 2. So this can be written as 6M upon A cube is equal to sigma given. Is equal to sigma given. Now the bending stress into is equal to M is the bending moment. I is again A to the power of 4 divided by 12. Now you tell me what is the value of Y. Your Y value is equal to half of the diagonal. Half of the diagonal. So for side A, the diagonal is how much? Diagonal is equal to root 2A. So this Y is equal to half of root 2A. So this can be written as half of root 2A. So which can be written as root 2 times 6M upon A cube, and 6M upon A cube is called as sigma. Means your sigma B into is equal to root 2 times this, root 2A times sigma. So C is the right answer to this question. Means 1 is stronger and 2 is weaker. Is it clear now? 2 is subjected to more stress compared to A, hence 2 is weaker. So 1 is stronger since less stress. 2 is weaker since more stress. Is it clear to everybody? Yes, my dear friend, is this clear to everybody? Yes, it's C. Let's proceed for the next question, my dear friends. A beam with a cross section given below is subjected to positive bending moment of 16 kilonewton meter. So the bending moment here is 16 kilonewton meter acting around the horizontal axis. The tensile force in the hashed area is, so what is the value of the tensile force in this? What is the value of the tensile force in this? So my dear friend, this is neutral axis. This is neutral axis. Neutral axis. So I know that the shear stress at this point is equal to 0. The top fibers are subjected to compression and the bottom fibers are subjected to tension. So your distribution is something like this. So this is what the distribution that you will be getting it. Is it clear now? But our interest is what? Our interest is only this much. So our interest is, let this be 1 point and this be 2 point. So your sigma 1 is equal to 0. And what is the value of sigma 2? What is the value of sigma 2? Sigma 2 is equal to m upon I into y, which can be written as m is 16 into 10 to the power of 6 Newton meter, Newton mm, divided by I value. I value is BD cube by 12. So it will be 100 into 150 cube divided by 12 and y value is 25. So can you tell me what is the answer to this? Sigma 2. What is the answer to sigma 2? $14.2. So your stress varies from 0 to sigma 2. So we should take average stress as 0 plus 14.2 divided by 2, which is equal to 7.1. So the tensile force is equal to average stress multiplied with area of the hashed area, which is 15 to 25. So the answer comes out to be 8.9 kilonewton. Is it okay? Uh, 16 kilonewton, sir. So 16 into 10 to the power of 3 for kilo and 10 to the power of 6, 3 for this. So this will become 16 into 10 to the power of 3 into 10 to the power of 3 Newton mm. Nagarajan, is it clear? Is this clear now? So y value we have to take it from here. Y is equal to 0 and here y is equal to 25. Is it clear now? And here y is equal to 75 and here also y is equal to 75. Aman, is it clear now? Yes, Nagarajan, is this clear? Since we are getting variable stress from 0 to 14.2, we have to consider the average stress. Which will become 7.1. If you don't consider average, you will get 17.8, which is also available there. Is this clear? Right. Let's proceed for one more question, my dear friends. A solid shaft of diameter D and length L is fixed at both ends. A torque T0 is applied at a distance L by 4 from the left head. Let this point is A, this point is B, this point is C. The maximum shear stress in the shaft is. So what is the value of the maximum shear stress? So T by J is equal to tau by R. So from this tau value is equal to 16T by pi d cube, right? This is the formula. Now they are asking what is the value of the maximum shear stress. 16T maximum divided by pi d cube, right? What is the answer? A is wrong. A is wrong. So what is the value of T maximum? So you see that when the shaft, now see at my hand. Yes, my dear friend, see at my hand. When suppose the shaft is fixed at both the ends, when the shaft is fixed at both the ends and I am applying a torque T naught here, I am applying a torque T naught here, you see that the portion AB will be twisted in one direction, whereas the portion BC will be twisted in another direction by the same angle theta. So theta of AB is equal to theta of BC since T naught is applied at L by 4 from one end. Is it clear now? If it is applied at the end point, then it will be different. But since it is applied somewhere in the middle, right, that is at a distance of L by 4, theta AB is equal to theta BC. So this I can write down it as TL divided by G into J of AB is equal to TL divided by G into J of BC. So from this I can say that this G and J get cancelled. T of AB into L by 4 is equal to T of BC into 3L by 4. So your L by 4 and L by 4 get cancelled. You can say that T of AB is equal to 3 times T of BC. So the torque in AB is 3 times more than T of BC. Is it clear now? T of BC. So your maximum shear stress will be equal to 16T of AB divided by pi d cube. So, but here it is T naught, but here it is T naught, but our answer is T of AB. Now find out the value of T of AB in terms of T naught. So when angle of twist is same, I also know that T naught is equal to T of AB plus T of BC. So from this, T of AB is equal to 3 by 4 times T naught, and substitute this value here. I will get the value of tau max as 12 T naught divided by pi d cube, and this is the right answer to this question. Is it clear now? So B is the right answer for this question. Nagarajan, please check the answer. Shivani, check the answer. Imtihas, Kajal, Ayan, check the answer, my dear friends. Is this clear? So since the torque T naught is applied somewhere in the middle of the shaft at a distance L by 4 from the left end, the torque in the smaller portion AB will be more than the torque in BC portion. Hence the stress in AB will be more than BC. But the answer is asked in terms of T naught. In terms of T naught, it is 12 T naught by pi d cube. How? 3 by 4. So T of AB plus T of BC is equal to T naught. So from this, what is T of BC? T of AB plus 1/3 of T of AB is equal to T naught. So from this, T naught is equal to 4 by 3 times T of AB, and T of AB is equal to 3 by 4 times of T naught. Is it okay? Imtiyaz. Vinay, please check it at my hand. you see at my hand, if shaft is fixed at both the ends and you are applying a torque in the middle, you see that the portion AB will be twisted by some angle in one direction, whereas BC will be twisted in another direction by the same angle. So because of that T naught at B, B will be twisted in both the directions. AB will be twisted in one direction, BC will be twisted in another direction with theta same. Is it clear now? Theta is same. So theta AB is equal to theta BC. I also know that T by J is equal to tau by R is equal to G theta by L. Tau by R is equal to G theta by L. So from this I can say that TL divided by G into J is equal to theta, and this I am taking up here. Is this clear, Vinay? So the torque in AB is 3 times more than the torque in BC, right? So today I am seeing that the strength is very less. I don't know why. So my dear friends, hope that you have understood what are the value of the normal stress, that is the bending stress in the beam, the shear stress in the beam, and the shear stress in the shaft also, my dear friends. So let me consolidate all the three. So in beams, your bending stress is equal to M by I into Y, and shear stress is equal to SA Y bar divided by IB. This is beams. Is it clear? This is beam problem. In shaft, the shear stress is equal to T by J into R, which is equal to 16T by pi d cube for a solid shaft. Right? And already we have seen axial bars, where your sigma axial is equal to P by cross sectional area, and the shear stress is equal to P divided by shear area. Is it clear now? So be clear about these three, whether it is a beam problem or a shaft problem or an axial bar problem. Naveen, since the tau maximum is asked to you, tau is directly proportional to torque, hence we have to take maximum torque. Since the question is maximum shear stress, so T is directly proportional to tau. So tau is directly proportional to T, hence tau max is equal to, is directly proportional to T maximum, hence T of AB. Is it clear, Naveen? Shaft is of circular cross section and bar is having an axial loading. So here the beam is having a transverse loading. Loading is like this. In axial bar it is having an axial loading, maybe the same cross section, and in shaft you will be having a circular cross section subjected to twisting moment. Is this clear now? Yeah, I have forgotten shear center. Let's see that tomorrow, if time permits, I will take that. Gaurav, I will take that shear center tomorrow. Don't worry. Tomorrow's class is the tricky questions in deflections. Along with that, I will also talk about shear center. Don't worry about that. Understood, Naveen? Yes, everybody, is this clear? Hope that you have enjoyed the session today, understood the difference between the axial bar, beams and shaft problems. What are the different types of normal and the shear stress in that? Is this clear? right? So my dear friend, don't forget to click the like button, press the bell icon, share this video, subscribe my dear friends, share this with your friends also. I will send the PDF, don't worry. So my dear friends, tomorrow is at 11 p.m. You will be having a tricky questions and deflection of beams. So my dear friend, please follow me on the app, Gradeup Super app. Follow me at Rushi Joshi, so that whatever these type of classes I am taking, it will be visible, my dear friend. So many classes I have taken, all that are available on the app. So I request everybody to please download the Gradeup Super app, go through the free classes which are available by the topmost faculties on Gradeup platform, my dear friend. So Gradeup is such a platform where all the dreams can come true, my dear friends, such as central government job, PSUs, MTech in IITs, MBA and MS. At present, Gear Up and Rank Up are the two courses which are running, my dear friend, for 2021, whereas Vision is the course which is running for aspirants preparing for ESE and GATE 2022, my dear friends. You can see the topmost faculties in the industries are with Gradeup, where along with me, Dheeraj Sardana sir, Ankit Joshi sir, Omkar sir, Chandrasekhar sir, Harshit Agarwal, Balaji sir are there to deal the subject of their expertise from basic, my dear friends. We are there, Gradeup faculties are there, Gradeup is there with you, so that we see that you will be here on this slide. So it will be very proud enough for us that whenever I take the class, very proudly I can announce about your ranks. Gradeup Super is a subscription model which will give an unlimited access to the structured live course and the mock test, my dear friend, through this green card. Right? So 3 months of subscription will cost you 9,000, 12 months 22,200, 18 months 30,600 and 24 months 36,200, my dear friends. Yes, Dharani sir, composite beams. Composite beams means we may have shaft in parallel, and shaft in series. Shaft in series. Is it clear now? Whenever I talk about the shaft in parallel, theta 1 is equal to theta 2, theta 1 is equal to theta 2 and the total torque is equal to T1 plus T2. Whereas in series, whereas in series, your theta is equal to theta 1 plus theta 2, but the torque T is equal to T1 which is equal to T2. Is it clear now? This is for series 1. Nagarajan, generally to get into the public sector undertaking companies, we should have below 500 rank. In order to get below 500 rank, our number of marks should be at least 80 plus. So if you get 80 plus, then only there is a possibility that you can get into PSU jobs. And average marks for good MTech or MS. So my dear friends, up to 1000 rank also there is a possibility that you can get into IITs, and up to 2500 you can get into NIT program, my dear friend. Is it clear now? So it depends upon your wish to which college you are interested, right? So if you want to go to the topmost institute, yes, below 500 it is needed, or ISC Bangalore is your dream college, then below 200 you require the rank. And if other IITs are there, yes, up to 1000 rank you can get into that, where the marks should range between 65 to 80, my dear friends. 65 to 80 should be the marks that you should get it to get into this IITs or NITs. Is it clear now? Hemant Nagarajan, is your doubt clear? Dharani? So my dear friends, SSC JEE के लिए अभिनव शर्मा, SSC JEE के लिए the classes which are going on our app are sufficient, my dear friends. The test series that we are giving are more than enough. That is more than enough for your preparation. उससे ज्यादा करने की जरूरत नहीं है. Okay, my dear friends, please take care of yourself and your family members, but don't forget to be in tune with Gradeup Super, which will give an unlimited access to structured live course and the mock test. Thank you and good night, my dear friends.